In order to complete major anomalies of ionization energy, the Lanthanide and Actinide contraction, Scandide contraction, that is the contraction in the size of elements arranged in the Lanthanide series, Actinide series, as well as in the D block elements, we need to understand relativistic effect. So here I am going to give a brief idea on the relativistic effect. This is not for the +1 +2 students, because it is only for the degree and PG students. So according to relativistic effect, this is purely according to quantum mechanics. Based on quantum mechanics, the relativistic effect is simply represented like when the atomic number, it is applicable only for heavier elements when the atomic number is greater than 70. According to Bohr theory, the Bohr theory concept, according to him, the electrons in the heavier elements attains, the velocity of electrons in the heavier elements attains the speed of light. As a result of that, the velocity of electron will be proportional to the nuclear charge. The magnitude of velocity of electron is proportional to nuclear charge, and as a result of that, as per Einstein theory of relativity, energy is equal to mc square. This is for a light where m is the mass and c is the light. Okay, c is the velocity of light. When this case is applied to heavier elements where the electrons, the inner electrons and as well as the outer electrons attains the speed of light half mv square. This is the kinetic energy. This is the kinetic energy of electrons in heavier elements, which is equal to mc square. So where c, the light speed of light attained by the speed of electrons. As a result of that, due to the velocity which is proportional to the atomic number, the nuclear charge increases. The nuclear charge increases means the electrons, especially the s electrons, that is in the 6th subshell or 7th subshell, because in heavier elements, the outer electrons are occupied in the 6th S subshell and 7th S subshell. In the case of lanthanides, in the case of actinides, etc. In all these cases, the S electrons, due to, as we discussed already, the penetration effect of S electron is very high, right? Because it has a symmetrical spherical shape and nucleus in the middle. So nucleus is symmetrically experiences its nuclear charge, electrostatic field on the s electrons. So in the case of heavier elements, the outermost 6s and 7s electron will shrink towards the nucleus, because the electron, according to Bohr theory, the velocity of electrons is proportional to the nuclear charge. So nuclear charge increases, it will experiences its nuclear charge. It's a force of attraction on the s electron because of its symmetrical spherical shape. Whereas there is another factor is there, the screening effect of 4f and d orbital. As you all know that the d orbital is having a flower-like double shape. F orbital, due to its F orbital, the structure is very complicated and it is having a dumbbell shape also. Due to an unsymmetrical dumbbell shape and non-favorable shape of 4f and 5d orbitals, the screening effect of F and d orbital is very poor when compared with the P and S. As a result of that, the screening effect of D and inner core electron F is very less. As a result of that, the nucleus force of attraction will pull the 6s electron towards itself due to the poor screening or shielding effect of 4f and d orbital subshells. The nuclear force of attraction pull the 6s or 7s electrons in actinides, 6s in the case of lanthanides, towards itself. As a result of that, the atom will shrink. The atom will shrink towards itself. It will be decreases its size. This shrinkage is the reason behind the gradual decrease in the atomic radii in throughout the lanthanide series as well as in the actinide series. The reason is that due to the higher nuclear charge and this relativistic effect of electrons in the heavier elements and poor shielding or screening effect of 4f and d or subshells and the spherical symmetrical shape of s orbital and its high penetrating power, the s orbital is shrink towards the nucleus and into its electrostatic field of attraction. As a result of that, the atomic size will be decreases. This phenomenon is called relativistic effect. This is a brief explanation about the relativistic effect. It is explained with the support of Bohr's theory that in heavier elements, the electrons attains speed of light, and applying the Einstein's theory of relativity, we can say that the kinetic energy of electron will be equal to the magnitude of speed of light. Okay, this is the relativistic theory. We are going to discuss the fourth anomalies of ionization energy, that is lanthanide contraction or lanthanoid contraction and actinide contraction. First, we will discuss the lanthanide contraction. Here, this is the series of lanthanides. I am not going to explain the configuration, but only the reason behind the contraction in the atomic size of lanthanide in this series. So, as you all know that in periodic table it is arranged from the 57th element lanthanide, the 14 elements are arranged at the bottom of the periodic table. So lanthanide is the 57th. From cerium to lutetium, all these 14 elements are arranged below the bottom part of the periodic table. Due to the last electron, the valence electron is moving to the f orbital. That's the reason. That is, the electrons which is getting added will move to the lower energy f subshell. So 4f0, 5d1 and 6s is the electronic configuration of lanthanum. And when we consider the 58th element cerium, the new electron will goes to F1 and praseodymium F3, neodymium F4 and so on. And as per the ionization energy and the periodic trend, from left to right, when atomic radii from left to right, atomic number increases, the effective nuclear charge also increases, ionization energy increases, and atomic radii decreases, right? This is the general trend. That is, the atomic radii decreases from moving from left to right or across a period. But here you can see that the experimentally determined atomic radius in angstrom, in the unit angstrom, cerium is 1.81, lanthanum is 1.83 angstrom, cerium is 1.81, and sodium is 1.82, and so on, 1.81, 1.99, 1.79, 1.80, etc. And the decrease in atomic radii is very, very less, and it is very gradually decreased. Not as we have discussed in the case of p orbital or s orbital or any other part of the periodic element trends. So the decrease in atomic radii is gradual and very less. And why this trend is going? This is called lanthanide contraction, and why this is happening. So this we can explain with the support of screening effect of F electron, F subshell, and excessive nuclear charge, and relativistic effect and penetrating power. These are the four factors that we can consider here. So consider this is the illustration of a shell, lanthanide shell. This is the nucleus, and this is the 4 of electron. and this is the D, and this is the S. This S electron is in the valence part, and D subshell is the penultimate shell. What is the penultimate shell? The shell which is near to the valence shell. And anti-penultimate shell is the third from the last. Third from 1, 2, 3. Third from the last shell, outermost shell. That is anti-penultimate shell. That is n minus 2. We can say it as n minus 2th shell. And this is n minus 1th shell. This is nth shell. So the anti-penultimate shell is 4f. This nucleus is experiences nuclear force of attraction to pull the s electrons towards itself. As you all know that according to relativistic theory, for heavier elements, the electrons attains the velocity of light, and the velocity of electron is proportional to z according to relativistic theory. Here, as also one more thing is that due to the spherical shape of 6s electrons and nucleus in the middle, the penetrating power means moving closer to the field of nuclear charge. The penetrating power of s orbital is very greater than that of p than that of f, and the shielding effect of this 4f orbital, the 4f subshell is shield the nuclear charge from by shield the nuclear charge from the 6s and 5d or the valence 6s electrons. As a result of that, the shielding effect order is s, p, d, and f. This is penetrating effect, and this is shielding effect. The poor shielding effect of 4f and 5d orbital, f orbital and d orbital, due to its unsymmetrical structure, they are having poor shielding effect. Due to the poor shielding effect, the s or subshell, the valence s subshell will shrink towards the nucleus. This will shrink towards the nucleus. As a result of that, the size will decreases. You can see that all the electrons in Lanthanide series, all the new electrons are added only onto the f orbital. So the electrons are added only onto the f orbital due to the poor shielding effect. The f subshell is having poor shielding effect. The shielding effect is small, but the nuclear charge increases due to the increase in atomic number. The 6s electrons, due to its high penetrating effect, it will be decreases. This will the reason behind Lanthanide contraction. Okay, so Lanthanide contraction is due to the very poor shielding or screening effect of F subshell, and high penetrating effect of S6s subshell. As the nuclear atomic number increases from cerium to lutetium, the nuclear charge also increases due to the poor shielding effect of 4f and high penetrating effect of s orbital. The nucleus will attract the valence s electrons towards itself. As a result of that, the size of valence subshell will shrink, which will a gradual, and when the atomic number, this gradual effect of nuclear charge also increases. As a result of that, the size decreasing, the trend of decreasing atomic radii will be gradually, and this is the reason behind Lanthanide contraction. Now we are discussing about actinide contraction. The relativistic effect is most prominent in the case of actinide contraction because according to relativistic effect and Bohr's theory, where the atomic number is greater than 70, the relativistic effect is very, very higher. So in the case of actinide series, the atomic number is starting with 90 thorium and ends at 103 lawrencium. So here the atomic radii, trends of atomic radii or ionic radii in the case of actinide is also similar like lanthanides, because the decrease is not general manner. It is gradual and is very, very less. See, you can see that in the case of thorium, in picometer, 10 raised to minus 12, 109 picometer is the ionic radius of thorium. When it's moving on, it is the decrease is very gradual, and at Lawrencium it is only 98 picometer because it is very less. This is because of the reason is behind the poor, very poor shielding effect of fine wave subshell. The shielding effect of 5F subshell, and due to relativistic effect and high penetrating power of 7s valence electron, the valence electron, the 7s subshell will move closer to the nucleus, and due to relativistic effect, the velocity of electron is proportional to nuclear charge, and which achieve the velocity of attains the velocity of light also. The velocity of light also, the nuclear charge also pull the outermost 7s electrons towards itself, so the size will be shrink towards the nucleus. And due to the poor shielding effect of 6d and 5f subshell, it is not at all prominent when we compare with the penetrating power and the nuclear charge. So across the period, the actinide series ionization energy increases, but radii decreases due to effective charge increases. So we can say that actinide contraction is mainly due to the reason the poor shielding effect of 5F subshell, because of which is very high, and the dumbbell shape, which is very inefficient to shield the electrostatic pulling power field of nucleus will applied onto the 7s, the spherically shaped 7s subshell. In addition to that, the penetrating effect of SO subshell is always very higher than that of other subshells because of its spherical symmetrical shape. So we can explain the Lanthanide contraction and Actinide contraction with the support of relativistic effect, penetrating power, and poor shielding effect of f orbital and d orbital. This and which decreases the atomic radii due to the increase in nuclear charge. Okay, very important part of our class, the consequence of Lanthanide contraction. You may face certain questions. Why a 5D series element showing similar chemical properties as that of 4D series? The reason is Lanthanide contraction. So here we are going to explain it. As you all know that there is a general trend that moving across a period, ionization energy increases due to increase in nuclear charge. Moving down a group, ionization energy decreases due to increase in the atomic radius. That's right? That's a general trend. So this is the 3D series. Starting from scandium, ends in zinc 30. Okay. And in the 4D series, starting from yttrium 40, ends in cadmium. And 5D series starting from lanthanum ends in mercury. Okay. But from lanthanum, after lanthanum 57, there is a 14 elements are arranged separately as we have discussed the lanthanide series from cerium to lutetium. Okay. In that case, the electrons from cerium to lutetium are moving to the f orbital. Okay. Followed by this lanthanide series, hafnium, tantalum, tungsten, etc., and goes to mercury. So, what the effect of lanthanide contraction on the similar properties of these followed elements with that of 4D elements? Okay. See, from scandium, moving from scandium, yttrium, and lanthanum down the group, the atomic radii of scandium is 1.64 angstrom, yttrium is 1.84, lanthanum is 1.87. That is common. That's the general trend. That is decreases as a general trend, and ionization energy also decreases. Whereas After lanthanide series, titanium 1.32, there is no effect. Zirconium, there is also no effect. 1.32, 1.45 general trend. But in the case of hafnium is the next element to lutetium. That is the very first element which follow lanthanide contraction, which is also having same atomic radii of zirconium. Okay, look at this 1.44, 1.45. And what about tantalum? The atomic radii of tantalum in the 5D series is 1.34, and that of niobium in 4D series also same. Tungsten also 1.30 is the tungsten atomic radii, but the molybdenum is 1.29. So the atomic radii of elements belonging to the 5D series show similarity, resemblance with that of 4D series element. This is the consequence of lanthanide contraction. Because of lanthanide contraction, due to the poor shielding effect of F electrons and the penetrating power of 6s valence electron and the relativistic effect of due to the relativistic effect of core electrons, the nuclear charge of lanthanides elements belong to lanthanide series increases, which pull the outermost electrons 6s outermost electron towards itself, which decreases the atomic radii of lanthanide series. That trends followed by the remaining 5D transition elements. This is the reason why they are showing similar chemical properties that of the chemical properties of 4D elements, which is evident from this case. You should note this one for giving an explanation for an essay type questions in MSc also. So you can explain with this figure. So it will give a full mark on that. So hafnium and zirconium is having similar chemical properties and similar atomic radii. Tantalum and niobium having tungsten and molybdenum is also having similar chemical properties and atomic radii also almost same. As a result of that, we can say that the atomic radii trend is 5D is greater or equal to 4D, greater than 3D. Okay, and effective nuclear charge will be 5D very much greater than 3D very much greater than 4D. Because of why I have written 5D is greater, because of lanthanide contraction, the nuclear charge is moving down. It is the general trend is nuclear charge decreases, but due to lanthanide contraction, 5D experiences very high nuclear charge than that of 3D and that of 4D. So we can generally mention it as the ionization order will become 5D greater than 3D greater than 4D. You should remember this case. Okay, the ionization energy order or stability order. The stability order of D block elements or transition metal elements or ionization energy order is as follows. 5D is always greater than 3D greater than 4D. This is because of lanthanide contraction. Moving down the group, the stability order will be 5D greater than 3D greater than 4D. And we arrived at this uh, uh, by adding these two concepts, the atomic radii and effective nuclear charge trends. So we have arrived finally at this. So you will face some questions like this. Mention or write the correct order from the below. So you may be given a different orders because maybe 3D greater than 4D greater than 5D. So you should remember this is the correct order. Okay.